In this video, we will see estimation of survival function using Kaplan-Meier Estimator. In the earlier video, we have discussed how to estimate survival function using actuarial method. So this is another method for estimating survival function. So suppose x is the variable that denotes time up to occurrence of a concerned event. So an event has been specified and we are observing the random variable which measures time up to occurrence of that specific event. Such kind of random variables cannot be handled using our regular analytical tools because there are some different concerns regarding these kind of random variables. The first thing, we cannot model this x as a random variable depending on time. That is, we cannot have regression model here, x versus t. That kind of setup cannot be worked out here because whenever we are using x as time up to occurrence of concerned event, it may not follow normal distribution. And therefore, since there is violation of normality, therefore we cannot use regression tool in this case. Secondly, most of the time x is never observed completely. As it is the time of the occurrence of concerned event, it may happen that a specific event may not occur even if our study time vanishes. So even if at the end of our study time, we may not get complete observation. So such kind of censoring is there for these random variables. So we don't have complete data on these kind of random variables all the time. And therefore the problem of censoring cannot be tackled using our regular analytical tools. And therefore there are separately designed methods to analyze these kind of random variables. And those methods are studied in survival analysis or time to event data analysis. So suppose x is following a certain distribution, the distribution structure is known. That is, suppose x is following exponential distribution, but the parameter of concerned distribution is not known, and that we have to estimate using sample data. So such kind of analysis is nothing but parametric analysis, where we know the population distribution. The only unknown thing is parameter concerned with population distribution. So such kind of analysis will be termed as parametric analysis, but in some cases it may happen that we don't have any information with regard to population distribution. So basically we have to estimate population distribution itself. So such kind of analysis is nothing but non-parametric analysis. So using survival data, we are going to estimate the population survival function, and for that there are two methods. One is actuarial method, the other one is Kaplan-Meier estimator, or also called as product limit estimator. So in this video we are going to study Kaplan-Meier estimator or product limit estimator for estimating survival function of the population. So suppose the data is given like this: x1, x2, xn, these are the lifetimes of n individuals. Now this is not the actual data. Suppose these are the actual lifetimes of n individuals. We may or may not be observing these lifetimes. These are the actual lifetimes. We may be observing these lifetimes, or we may get censored before observing these observations, before taking these readings. So with each xi, we are assigning a random variable ci. It will be known as censoring variable. And now what we will be observing will be ti. We will not be observing xi directly. We will be observing ti, which will be minimum of xi or ci. So xi is the actual lifetime. Before observing actual lifetime, if ci is the censoring variable that is less than xi, then we will be observing ci as the observation on that particular ith individual. If ci falls beyond xi, then we can have complete observation on xi. So whether we are getting complete observation or not, to denote this, we have taken a random variable delta I. So delta it is working as an indicator. So if delta is equal to 1, then yes, in that particular case we are having a complete observation. Having a complete observation is success for ourselves, and therefore delta I is equal to 1 is used to denote success. So delta I is equal to 1 will be the success for ourselves, that is the observation will be complete. It means the censoring time Ci will be greater than Xi. But if Ci is less than Xi, then that observation will be censored, and therefore delta I will be 0 in that particular case. So suppose the situation is like this: C1 is less than X1. So X1 is the actual lifetime of first random variable, first unit. But we may not observe X1 in this particular case because the concerned censored variable is at C1. And since it is at C1, C1 will get observed first. That is the first unit. Even if it fails at X1, we will not be able to observe it up to X1. We will not be able to observe it beyond C1. So C1 is censoring time. So first unit will get censored at C1, and therefore we will have measurement T1 as equal to C1 itself. In some cases, it may happen that C1 is beyond Xi. So in that case, we'll be observing X1, that is complete lifetime will be observed in that particular case. Therefore T1 will be equal to X1 in this case, or in general Ti will be equal to Xi as Xi is less than Ci. And correspondingly delta I in this case will be 1 as we are having complete observation. If we are not having complete observation, that is if Ci censoring happens before the actual failure, then delta I will be equal to 0. So now suppose T1, T2, Tn, these are the things that we have observed. These are not the actual failure times. So we will not be provided with X1, X2, Xn. These are the actual failure times, but we will not be provided with X1, X2, Xn all the time. We will have the data on T1, T2, Tn, where T1 may be the actual failure time of first component, or it may be the sensor time of the first component. Similarly, T1, T2, T3 up to Tn, these readings can be interpreted. So suppose whatever we have observed T1, T2, Tn, these times we have ordered in order of their magnitude. So we are having order statistic structure corresponding to the observed sample T1, T2, Tn. So we'll have T bracketed 1, T bracketed 2, T bracketed n. So T bracketed 1 is not the time at which first component has failed, because now we are talking about order statistics. This is the first occurrence time, and that occurrence may be the death of individual, maybe the failure of a component, or it may be sensory. So first thing happened is at time T bracketed 1. That may be concerning with respect with first component, or it may be concerned with fifth component, and so on. So these are the order statistics: T bracketed 1, T bracketed 2, T bracketed n. Correspondingly, since we are having a continuous setup, suppose the lifetime of random variables, if we assume those to be continuous, then there are very less chances that two events will occur at the same time, and therefore we have considered this as T bracketed 1 strictly less than T bracketed 2, which is strictly less than, and so on. So we have avoided the case of ties. So no two events will happen at a given point of time. Therefore we have considered strict inequality. T bracketed 1 will be strictly less than T bracketed 2, which will be strictly less than T bracketed 3, and so on. And lastly, T bracketed n minus 1 will be strictly less than T bracketed n. We have ordered the data T1, T2, Tn. Correspondingly, we'll order the data on delta 1, delta 2, delta n. Now here the important thing to be considered is delta bracketed 1, delta bracketed 2 up to delta bracketed n. These are not the order statistics corresponding to delta data. These are the statistics, these are the imposed values by the order statistics corresponding to T1, T2, Tn. It means that delta bracketed 1 is the value of delta on the component for which T bracketed 1 is observed. That is, if t bracketed 1 is actually the reading on fifth observation, then delta bracketed 1 will be the delta value on fifth observation. In general, if t bracketed I, if ith order statistics in t data is actually the reading on jth unit, then delta bracketed I will be directly taken to be delta j. So delta bracketed 1, delta bracketed 2 up to delta bracketed n, there may not be proper order among them. This is the order imposed by t bracketed 1, t bracketed 2 up to t bracketed n. Now we'll define some terminologies. Suppose R of t. Suppose t is a specific time point, then R of t will be the risk set at time t. At any given point of time, there may be some individuals which are exposed to death. So those are the individuals that are having the risk of getting died, or those are the components that are having the risk of being fed. So collection of all those individuals or units will be a risk set because they are forming the set which is at the risk at that specific time point. So R of t is risk set at time t, which is the set of subjects still alive at t minus. You are exposed to death only when you are alive. Therefore, alternatively, this is the set of all those individuals which are alive just prior to time t. So just before time t, the individuals that are alive in the system, those are at the risk of getting died. And therefore R of t will be the set of subjects which are still alive at time t minus. Now n, suppose R of t, similarly we can define R at t bracketed I. Since we have fixed these time points, consider time points as t bracketed 1, t bracketed 2, t bracketed n. So correspondingly, like R of t, we can define R at t bracketed I. So if we consider t bracketed I as some time point on time axis, then R at t bracketed I will be the risk set at time t bracketed I. That is number. It will be collection of those individuals which are alive just prior to time t bracketed I. So once that set is formed, we can measure cardinality of that particular set. So how many individuals are there in the risk set, or how many individuals are there which are exposed to death at time t bracketed I. That will be denoted by Ni. So Ni is the cardinality of the risk set at Ti, or alternatively it is the number of individuals which are alive at the time t bracketed I minus. Now exactly at time point t bracketed I, there may be a death or there may not be a death. So how many number of individuals have died at time point t bracketed I, that will be denoted by Di. So Di is nothing but number of individuals died at specific time point t bracketed I. Di, this can take value 1 or 0. Actually there is no need of writing d bracketed I, just Di is enough. So Di can be 1 or Di can be 0. Since we have not considered data with ties, therefore at a given time point a death can happen or there cannot be death at that specific time point. Therefore number of deaths will be either 1 or 0. There cannot be 2 or more than 2 deaths at the same time point, and therefore Di will never take value 2 or greater than 2. Now suppose the time region that we are considering is 0 to t. Now in actual method of estimator, we have considered this given time interval and we divided it into equal sub interval. So while dividing it, we considered, suppose 0 to t is the entire region, and suppose we want to divide it into 10 sub intervals, then this entire region will be divided into 10 equal sub intervals. Accordingly, those nodal points or threshold points were determined. Now here we will not have equal sub intervals. Here the division of this entire interval will be done based on the readings. That is what readings we have got on t data. That is t bracketed 1, t bracketed 2 up to t bracketed n. By considering these as threshold points, we will divide the entire region into sub intervals which may or may not be equal in length. Most of the times they are not going to be equal. So this entire interval will be divided by considering t bracketed 1, t bracketed 2, t bracketed 3 and so on up to t bracketed n as the threshold points. So accordingly there will be n sub-intervals. If we are having n observations, then there will be correspondingly n sub-intervals. These sub-intervals will be denoted by I1, I2, I3 up to In. Now t bracketed 1, this is the first event time, and that event may be actual death or that event may be getting censored. So we have to be aware that t bracketed 1 whether it is a death point or whether it is a censored point, and therefore to denote this we have used t front symbol. So t bracketed 1, t bracketed 2, these time points will be denoted by some symbol. So t bracketed 1, here we have denoted t bracketed 1 by cross, t bracketed 2 by follow circle. So t bracketed 1, it has been denoted by cross. It means that the observation is censored. So whatever first observation, whatever the observation we have considered at t bracketed 1, so that is a censored observation. The concerned unit has not died at that particular time point, but it got censored at that specific time. If we consider t bracketed 2, then this is the time at which concerned unit have died or concerned individual have died. So t bracketed 2 is the actual reading of failure time. T bracketed 3, again it is censored time. T bracketed n minus 1, again it is censored. T bracketed n is the actual reading, that is, this is the point at which concerned unit has been died or concerned individual has been died or concerned unit has been failed. Now once we have found these intervals, we'll find Pi for every interval. Pi will be the probability of surviving through that specific interval. Once we know that the individual or unit has entered in that particular interval. So Pi will be the probability of surviving through interval I, given that it was alive at the beginning of I. So suppose if an individual has entered in the year 2021, what are the chances that it will survive throughout the year 2021? That will be denoted by I 2021. So similarly, it will be denoted by P 2021. So similarly, we are having Pi. It will be probability of surviving through that specific interval I, given that it was alive at the beginning of II. So once you enter in that specific ith interval, what are the chances of getting through that interval II? So Pi will be the probability that T will be greater than T bracketed I. T greater than T bracketed I, it means that T, that unit, has survived beyond ith interval. This probability is conditional probability with conditional information, as T is already greater than Ti minus 1. So T already greater than Ti minus 1, it means that whatever lifetime of that individual is, that is going to be greater than Ti minus 1. That is, it is going to enter into ith interval. So if it enters in ith interval, what is the chance that it will survive through ith interval? That probability will be denoted by Pi. Correspondingly, Qi will be probability of not surviving to II, given that the individual or unit was alive at the beginning of II. So if a person has entered in the year 2021, what is the chance that it will not survive throughout that year? What is the chance that the individual will die during the year 2021? That probability will be denoted by Qi. Now if there are say 10 individuals who have entered in the year 2021, and unfortunately say 4 individuals died during that particular interval, then a genuine estimate of Qi will be 4 divided by 10. Out of 10, 4 individuals died. So what is the probability of not surviving through that interval? It will be simply 4 divided by 10. Therefore, that estimate of Qi can be easily determined as Di upon Ni. Ni is the risk set, cardinality of risk set. These were the individuals that were exposed to death, out of which Di got died in that specific ith interval. Therefore, Qi cap in estimate of Qi will be simply Di upon Ni. Accordingly, estimate of Pi will be 1 minus Di upon Ni. Now, since we have considered data with no type, that is Di can be either 1 or 0, therefore Pi cap will be simply 1 minus 1 upon Ni. If the observation at that ith time point, t bracketed I, if it is uncensored, that is if it is complete, that is whatever we are observing there is the actual death time, then Di will be equal to 1 and therefore Pi cap will be 1 minus 1 upon Ni. If the observation is censored at that specific time point, so no death has been occurred at that specific time point, then it will be simply 1 minus 0 upon Ni. That means it will be simply 1. So this will be the estimate of Pi cap. Now S cap at T. So T is some specific time point at which we want to estimate survival function. What will be the value of survival function at this specific time point? So in order to determine this specific estimate, we have considered the quantity 1 minus 1 upon Ni for every Ti which is less than equal to T. So you have to survive through each and every time point before T in order to get beyond T. So if T is a given time point, whatever Ti values are there before T, you should get surpassed to all those Ti values, and therefore this is considered to be product of 1 minus 1 upon Ni. All those values, all those Ti values you should go beyond, and therefore it will be simply product of 1 minus 1 upon Ni, and this product is taken over all uncensored observations, and uncensored observations, that is Ti, and it will be for those Ti which are less than equal to T. This can be rewritten as 1 minus 1 upon Ni raised to delta bracketed I. So instead of focusing only on set of uncensored observation, now we have considered in general, and therefore that uncensored U symbol below the product sign has been vanished, and as a penalty we have considered delta bracketed I as the power of 1 minus 1 upon Ni. So if there is censoring, then delta I will be equal to 0, correspondingly 1 minus 1 upon Ni raised to 0 will be 1, and that term will vanish. So virtually we have done nothing, both these terms will be equal. Now if there were n individuals at the start of the experiment, and at every time point I, if one individual is going out of the system, either he dies or he gets censored, so at every time point we are losing one individual. So whenever we are reaching at time point I, then we must have lost I minus 1 individual, and therefore Ni will be simply n minus in bracket I minus 1. By simplifying, it becomes n minus I plus 1, and therefore it simplifies to product of 1 minus 1 upon n minus I plus 1 raised to delta. So this will be the estimate of survival function at time point T, and this is Kaplan-Meier estimator of survival function. Thank you.